All right. Well, hi everybody. How are you? I hope you're having a great DevOps Days, Tel Aviv. I'm really sorry I couldn't be there in person. I really wanted to go, but unfortunately, I wasn't able to get a flight from the US. But I'm happy we're connecting online. I'm very looking forward to my next visit to Tel Aviv. But I'm here to tell you about the real story of 30 seconds of silence, a scary event that happened to us a few years ago that I want to retell today. It was a regular day in our clusters. Deployments were getting created, container images were pulled, pods were starting. Everything was fine. It was a great day until at some point, for 30 seconds, everything froze. Our deployments were being created, our pipelines were happy, but no image was getting pulled. None of our pods were able to start. For 30 seconds, nothing happened. And then all the alarms starting to go up on our PagerDuties. My name is Ramiro Berrelleza. I'm the founder and CEO of Okteto. And as I said, I'm here to tell you the story of those infamous 30 seconds of silence. That QR code will point you to my website. I will publish the slides there after the talk. And it also has a link to all my social media accounts if you want to connect after the conference. I would love to chat with all of you, talk about open source, software development, dev experience, and all those beautiful things. So 30 seconds of silence. Before I get into it, I just want a high description of what is Okteto, because this happened to us in our own clusters. So Okteto is a platform that enables everybody in your organization to easily deploy development, test, and preview environments that look like production. This runs on Kubernetes. We have a SaaS product, so we run this for our customers. Our customers depend on our environments being up and running for them to develop. So that's why you can imagine the fear when we see, like, for 30 seconds, nothing is coming up. I have to warn you that this is a true story. So we'll go through it. I'll show you what happened, how we solve it, and hopefully we'll all learn something together and we can decide if our clusters were haunted or if it was really just a bug in our code. So let's start by the facts of what happened on that terrible, terrible night. We were able to kind of put all this together after the fact. So we had our clusters, they were running fine. At some point, one of our nodes scaled down, standard Kubernetes behavior. We had a low workload, so the cluster scaled down and those workloads moved somewhere else. So you can see the pod was scheduled, was correctly, it was assigned to a node. But then we saw this message: image not found, or it's private, or image pool secrets is not properly configured. You can see that it was going on for a few seconds until it just started to work well again. You can see here we got a bunch of different errors. Not found. Is it private? Is the secret missing? Then it wasn't able to pull it. Then it was backing off. And then after 30 seconds, it just went and started behaving correctly. This happened across multiple pods. It was not just a single thing that happened. So it really got us like scared, like what's going on? Is our cluster haunted? Are we just seeing the work of some evil spirit? Or most likely, was there a bug in our code, in our deployment workflows, or whatnot? You know, being the good engineers that we are at Okteto, we could not let this go. So we assembled a team of ace detectives to figure out what happened. Why did we saw those 30 seconds of silence? So we went at it. We identified, hey, what could have happened that caused this? So of course, if you remember going back to the Kubernetes secret, the Kubernetes error message, the first thing we saw was that, hey, maybe the image pool secret is missing. That's what the actual error said. So that was our first target. So for those of you not super familiar with Kubernetes, how does an image pool work? You know, when a pod starts on a node, and then you need an image. The image is to be pulled. So you have a node, you have a registry where the image is being stored. You have in the node, you're going to have container D running, and container D is the one that's actually going to pull the registry from the image. For those of you experts in the room, I am oversimplifying things a bit for sake of clarity. So forgive me if I miss some details. But the image gets pulled from the registry and gets placed on the node. Especially when there's a new node, you're going to see this happening a lot. If the image is private, which is our case because we run an internal registry in Okteto, you also need to have credentials. These credentials, container D is going to get the credentials, is going to use them to call the registry, and then get the token. And the credentials in Kubernetes, there are different ways to define them, but for me, one of the easiest, best ones is you have the secret on a namespace. That way you can give different namespaces, different access levels to your registries. And it's something like this. It looks very similar to a Docker config file. So it's Docker config JSON that Docker uses on your desktop, but this one is running on the cluster. So we went, we checked, and everything was there. We had the image pull secret. We had the service account. Everything was bound, and the pod was there. If you remember from the logs, we saw the pod was running. It was having issues pulling, and then it worked fine. So it was very strange. Everything was there. Everything was created beforehand. As you know, Kubernetes it's async. So sometimes resource creation can cause this kind of problems. But in this case, it didn't. Everything was there. So we were like, okay, it's not the image pull secret. What could it be? Let's keep digging into this. And now we saw this image not found, our second potential monster here. Was the image missing? In Okteto, when you deploy a dev environment, there are three components that get involved here. We build the image, we store it in a registry, and then when Kubernetes runs the deployment, it pulls the image. So fairly simple, it's very straightforward, easy to trace. We have logs from every stage. So we knew that build happened, that the image was pushed, it was stored on the registry. We were able to check that the image was there. If you remember, eventually, after those weird 30 seconds, it was able to be pulled. And then the deployment was able to eventually find it. So again, very strange. We went to our logs, we went to like error messages, nothing there. The registry was running all the time. The build pipeline didn't have any errors, no glitches there, no retries, none of those things. But still, the image wasn't able to be pulled for 30 seconds. So at this point, we're kind of like starting to go like, maybe the cluster was just haunted. Maybe it was just one of these things that happens for 30 seconds. Are we going to have to always be in the watch for these 30 seconds? But people in the team were like, no. We have to keep going. There's no such thing as a haunted cluster. Something must be going on. So the next thing we went and checked was the registry. Maybe there's something on the registry that didn't find the image. Maybe the storage that we're using got disconnected for a little bit. Layer was corrupted. There's always many things that could happen there. So it was like, is our registry just haunted? Is that the piece that's having issues and giving us this 30-second delay? So going back to this, you remember we have the node, we have the registry, we have the credentials, and you have container D driving all of this. Now, something different that Okteto has, we thought, okay, we have our own authentication system. This is a plugin to the open source registry where you can ask the registry to authenticate with something external, an API, to validate if somebody has access or not to an image. We use a special logic because we want, in our case, to be able to manage the permissions per user, per namespace, per cluster, all these things that we abstract to all the developers, but that internally matters a lot, especially when you're running this for multiple customers. So we went deep there. Look at the logs of the registry, look at the logs of our authentication service, but everything was working fine. We didn't see any 404s, in case when the image cannot be found. We saw a bunch of OKs, 200 OK, the standard HTTP codes. And then we saw a 401, which is, okay, authentication denied. We thought maybe, okay, 401, maybe this is causing the image issues. But no, as we kind of like read through the logs, as we kind of consulted some experts on the authentication protocol for the registry, we determined no, that is a standard behavior. That's the way the containerd works. They will try to pull an image, it will try different permissions until it finds the right set of permissions. So it wasn't the registry. At this point, we were, I'm not gonna lie, kind of going crazy about this. It became an obsession, but we also wanted to make sure we did the right thing. But we were running out of ideas. We were like, it's not image pool secrets, it's not the registry, it's not the node, it's not happening again. So what is it? Is it just one of those ghost in the machine kind of scenarios where something happened once, blame it on solar flares, blame it on a ghost? But the team started to take this personal, be like, no, 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 we cannot give up. We don't want to just go home defeated. We don't want to like live in fear that this 30 seconds will always kind of like haunt us. So we wanted to keep going. So everybody kind of got into a virtual room. Our company is remote, and kind of kept going over ideas of like, what could be happening here? What did we miss of our analysis? That is, we must be missing something. So what we did at that point, after having a lot of coffee and maybe a walk around the block to kind of like get our brains going, we went back to the whiteboard, the virtual whiteboard, and kind of looked at the spooky facts. What happened? What do we know? And we kind of put together this chart. Stuff in the top is what happened on the node before it scaled down. Stuff at the bottom is what happened on the node after the scale down event. We're going to simplify them by calling them node A and node B. So what we know is that on time 0, node A started the shutdown sequence. So it evicted this pod for the dev environment to a new node, then it scaled down the node. Then on node B, a new pod was created. The image failed to pull on node B. It retried, backed off, retried, and after 30 seconds, it was able to successfully pull it. And we saw that across multiple pods, not just this one, but we wanted to isolate to like figure out, okay, what happened for this one? And then maybe we can understand what happened to all of them, because we were talking about probably 50, 80 pods that had that issue for 30 seconds. And, very annoying, but also we want to make sure that this doesn't happen again. We don't want to affect our customers. And, we want to follow all the best practices. We are a company that prides itself on following all these standards of following good DevOps practices. And that's why we wanted to kind of keep going and understanding what happened. So this was our basic timeline of what went that day. So we kind of looked back at it and said, okay, we talked about the registry, we talked about secrets, but we haven't really looked into containerd itself. Containerd is a very solid piece of software. It's used everywhere. But maybe there's something there. Maybe the latest version, you're always blaming other things. No, maybe the latest version of Kubernetes has a new version of containerd that has a bug. Maybe we miss a setting when we set up the clusters, things like that. So we went back to understand what was containerd doing in this timeline. And when we looked at the logs on containerd itself, which it's not that easy, you have to dig through a lot of things to get there, we found this. We saw that after the pod was placed on the new node, we started to see this error, 4.1 here in the diagram, pull connection refused. Like, okay, something happened during the pull. Great, maybe not a ghost, maybe there's something real here. And an IP, 10.1.0.89, port 443. We're all up to date on our IP allocation, so we know, hey, this is a private IP. This is probably coming from our cluster, looks that way. Port 443, okay. SSL, something is pulling internally, okay. So then the question was, okay, who is 10.1.0.89? Where is this IP coming from? Who does it belong to? We looked at Kubernetes, kubectl, get services, and most of this troubleshooting we did was just done on kubectl commands, which, is a very powerful tool, not the easiest, but kudos to the team at Okteto who are experts at this. It was amazing to see them do all this. And then after trying a few different CLI commands, we ended up with, okay, 10.1.0.89 is the internal IP of the load balancer used by our Ingress Nginx controller. Okay, we're getting somewhere. The internal IP, failed to connect. But why? It's been working well. It's a solid piece of infrastructure. Everybody uses Nginx controller. We know it's very powerful. So what happened there? So to kind of go through the next step of what happened, I'm gonna just take a little sidestep to explain something about how Okteto works internally. At Okteto, we use Nginx controller heavily. We use it to expose dev environments. So you can have a publicly accessible URL for your dev environment where you can access and use the applications you're developing. But we also use this load balancer to load balance the registry, the build service, our APIs, and a bunch of other things. In the early days, we just kind of had the load balancer and the registry in front, like this diagram. However, as you can imagine, moving images is expensive. Moving images on public cloud through external IPs is even more expensive. So this pool you can see here of the node going through the load balancer to kind of get the image and then get it into the node was very expensive. So years ago, actually, we ended up doing an optimization where we're gonna had a daemon set that would update the etc hosts file on every node of our fleet to point the load balancer's DNS to the internal IP and not the external. So imagine you have company.okteto.dev, but instead of pointing to our external facing IP, imagine something in public range, 34 point something, is pointing to, as we saw, 10.1.0.89. We do this because the load balancer IPs don't change that often. They're fixed. We're using fixed IPs there. It's more efficient, and it allows us to go through the internal network, which is cheaper. You don't have to pay. In this case, we run on GCP as much for network. So it was an optimization that we've been using for years. So that's where the IP came from. Like, okay, now we know that there's something on Nginx and the node, something in the network in between that didn't really work well. So, we jumped into the node, start running DNS solutions because, as we all know, it's always DNS, or maybe. And we had the registry was resolving, Okteto was resolving the right IP, everything there was fine. So that was correct. So what we realized at that moment, as we were looking at Nginx is, of course, Nginx runs on almost every node in Okteto. When the pod got evicted, the Nginx ingress also got evicted. So we had these two pods or multiple pods, but ingress controller moved to node B. The pod also moved to node B, but there was this connection that was refusing to be responded. So I was like, what happened? So here's where we kind of had to go back to the basics of understanding how services, load balancers, and Nginx controller works on Kubernetes. An important aspect, to me, one of the most important aspects of Kubernetes is service discovery. Is one of the, if you're all like me, you've been around for a while, that used to be a huge problem. There was a bunch of different products, Consul and a few others that solved this in the past. And then Kubernetes came and gave us, in my opinion, a very elegant, easy to use solution. And how internally the way it works is there is an API that will give you the endpoint information of a service. It's going to be based on labels and based on queries and based on is the pod ready? So for example, here, if you have two instances of Ingress controller, two pods, and you fetch the endpoints, Kubernetes is gonna find the labels. It's gonna give you the IPs of these two pods, so that you can use them to call them through the request. When one of them goes bad, when it gets evicted, if it's not ready, if the health check is failing, if it's on a restart routine, when you fetch the endpoints, you're only going to get the endpoint of the one that's active. Makes sense. You only want to talk to a pod that is active. This is the default behavior. You don't have to do anything for this to work. It's super resilient and is one of the core pieces of Kubernetes. Now, there's no magic here. Behind the scenes, what's happening is a mix of like IP table management, DNS resolution, all of those things, right? So internally, what happens is that every node on Kubernetes has a kube proxy, or at least our clusters. If you're running on CNI with other plugins, it might be different, but the default on GCP, you're running kube proxy. And kube proxy, instead of having to pull this IP information on every single request, because this takes time and you want your request to be as fast as possible, kube proxy will be watching every endpoint, will be keeping a list of it, and as they change, it will update IP tables. And the moment we kind of saw that, we're like, I think we know what's going on. So one very particular thing about Kubernetes and about Linux, right, is that IP table updates are not free. When you change them, and if you have a lot of pods, imagine you're running a cluster with thousands of pods, thousands of services, we do, you would have to update the IP table with thousands of services. So if they're changing very often, if you're very dynamically deploying things, relaunching, this might take a while. So kubeproxy, very smartly, in my opinion, has a throttle of how often kubeproxy will update IP tables. And by default, you can modify this, but by default on GCP, it's done every 10 seconds. So it'll get the information, it will watch the IP changes, it will keep them in memory, and every 10 seconds, kubeproxy will then update the IP tables, flush them, and go at it. And this happens every 10 seconds. You can modify this. I don't recommend you do, but you can do it. So maybe you know where I'm going with this. But if we go back to our timeline, we had the pod evicted on time 1. We had ingress controller evicted on 1.1. And then we had the really bad luck that on node B, on time 1.2, IP tables were flushed. Then new pod came up on point B, and everything here takes sub-second. Then when the new pod came in, the image wasn't able to be pulled because of connection refused. And what happened was that because we were within this 10 seconds while kubeproxy was waiting to flush the IP tables, node B still had the IP of the pod, of the ingress nginx controller pod on node A, and was trying to talk to this now gone pod, which is why you got the connection refused. It tried a few times, it failed. Container D got into their fallback logic of like, okay, let me wait a few more seconds. And after those 10 seconds happened, after the IP tables were flushed and the node had the new IPs, then we were able to pull the images and everybody was happy. So for those 10 seconds that ended up being 30 because of like retry policies and just sheer bad timing, everything went back to normal. So at this point, we were like very excited. Oh my God, we found the issue. We were like super happy. The engineering team, this is really good detective work. And we were very satisfied. We're like, yeah, we know what happened. The 30 seconds of silence was because the node was talking to a stale IP table. So it was ingress nginx or IP tables, name it whatever you want. But we found our culprit. Our cluster is not haunted. We know it was something that was causing it. And then 5 seconds later, we're like, okay, but can we fix this? This is a pretty deep thing in Kubernetes. Or are we just doomed to always wait for this 30 seconds that might come or not? Like, do we have to put garlic crowns in our doors so that these vampires don't come on knocking and kind of like affect our customers? Well, we were not willing to do this. We wanted to do something. So I'm going to go through this really quickly, what we ended up doing to prevent this from happening. And knock on wood, but in 2 years, it hasn't happened ever since. So what we kind of discovered, we didn't know about this feature of Kubernetes, is that when you delete a pod, there's a sequence of events that happens. And in Kubernetes, most of them are async. So you have the kube controller that will refresh the endpoints. You have kube proxy on the nodes that, as we saw earlier, is going to pull the IPs, flush the IP tables, do all those things. The kubelet is going to send a SIG-term signal to the pod. It'll give it 30 seconds to shut down. And then after 30 seconds, it's going to kill it. This is your standard sequence when you delete a pod. However, there's a feature in Kubernetes called pre-stop where you can configure your pod so the kubelet will send a pre-stop signal to your application instead of a SIG-term. This allows you to run custom code as your shutdown sequence. And then, after that sequence is done or there's a timeout, you're going to get a SIG-term. And then your SIG kill. So it kind of adds this pre-stop, I guess, before SIG-term and SIG kill come into the picture. In the case of Ingress Nginx, there is a hook. It's called wait shutdown that now we're using to help us handle the sequence more gracefully. And you can see the code. This is a screenshot out of Nginx's Ingress Nginx code. You can see that what the wait shutdown signal does is it will send a SIG-term directly to the Nginx Ingress controller that is running, not to the pod, but directly. And then it will wait, and then it will terminate. The way this works and what this is very useful is because this allows you to kind of use this pattern where you're accepting new connections. The moment the pod starts the sequence to be deleted, you can stop accepting connections. Nginx does this already out of the box. And then when things are done, it'll be accepting connections on the new pod. So what we ended up doing, and I kid you not, is we updated our pre-stop code. We added a 10-second sleep before running wait shutdown to add that extra slowness to prevent us from hitting this cycle of being in between IP table refreshes. We could have done it random, maybe. Maybe we could have done something more sophisticated, but we tried that. It worked. And for the last 2 years now, I think, we have not seen this issue again. So not the most elegant of solutions, but hey, it works. And as an engineer, I'll take a solution that works over something super elegant and theoretical. So very excited about the team. They applied the solutions. We run a bunch of tests. We amped up our telemetry for a bit to make sure that we got alarms if these issues ever showed up again. And so far, no more 30 seconds of silence. We run even more clusters than before. We run more dev environments than before. And at least this particular issue hasn't shown up again. Now, you accept connections. When it's kind of flushing, we stop. And then it just became much more reliable and much efficient because of pre-stop hooks and because of this artificial 10-second sleep that we added. Want to clarify, this works for us because we know our system, because we know our times, because we know how those things kind of play together. I would not recommend this as a general solution, but I think it's something that is great for all of you to know about, to have in your toolbox. And maybe if one day you see that your images are suddenly not pulling for 30 seconds, well, you know that it's not a ghost. You know that it's not bad luck. It's not because it's Halloween. It's not because it's Day of the Dead. It's because maybe Ingress Nginx or maybe something else. What's important about this is the power of investigating what went wrong, the power of understanding all the pieces of your platform, the power of experimentation, because I still believe that there are no ghosts haunting clusters. There are only bugs, people, and of course, DNS, or in this case, IP issues. And that's all I have for today. I hope you enjoyed the retelling of this true story of the 30 seconds of silence that drove us mad, first of confusion, then of happiness, and what happened that day in our cluster feed. I hope you find it entertaining. I hope you learned something today. I hope you never have to go through this, but if you do, remember, IP tables get flushed every 10 seconds on Kubernetes, and something like a pre-step hook can help you avoid that trap. Thank you, everybody. It was great seeing you online. I hope you're having a great DevOps Days Tel Aviv, and I am looking forward to seeing you in person soon. I'm going to be in KubeCon. If any of you are going to KubeCon, please send me a message, Twitter, LinkedIn, any of those works, Blue Sky now, because I would love to meet you in person. Thank you very much. And I don't know if we have time for questions, but I'm here.